let us talk about relativity or reality, a dialect of time. Here we will be discussing about Einstein's relativity based on time, which behaves differently for different people based on location of the people in space-time curvature. We'll see that with a simple thought experiment and three cases, and we'll come to a conclusion with the end of the video. First we will be considering the thought experiment. We'll be traveling from A to B. Let your house be at A, at location A, and the library is at location B, which is exactly 1 mile from your house. You can travel from A to B by walking or by driving through a car. And the third case, famous Einstein thought experiment, by riding alongside a light beam. Let us see that thought experiment. In the first case, we are traveling from A to B. We are walking at 3 miles per hour, and in the second case, we choose to travel by car. The car travels at 70 miles per hour. In the third case, we are riding alongside a light beam, and the photon originates from your house and reaches the library at B, and we are calculating the time. We will be considering the sub cases individually and will find the time. In first case, we are traveling by walking at 3 miles per hour, that is 8.33 into 10 minus 4 miles per second. At this speed, we will reach 1 mile, that is we will reach the destination of library at time 1200 seconds. The math is shown here. Time is found by distance by velocity, and we get 1200 seconds or 33 minutes. That is somewhat okay. Let us see the next case. In the next case, you are traveling by car. The speed of the car which you are traveling is 70 miles per hour. The time is found to be 0.0142 hour or 51.4 seconds. That is, in the previous case, by walking we need 33 minutes to reach the library. By traveling by car at 70 miles per hour, we reach the library in less than a minute, 51.4 seconds. Okay, that's fast. Let us see the next case. In the next case, we are riding alongside a light beam at the speed of light. So the speed of light is 670,616,629 miles per hour in terms of miles per hour. So to reach 1 mile, that is to reach the library, the photon has to travel at the speed of light. To cover 1 mile, the time taken is 5.36 into 10 power minus 6 seconds. That is exactly around 5 microseconds. That is very, very low. In the first case, by walking 33 minutes. In the second case, by driving a car 51 seconds, I think. In the third case, it's 5 microseconds. You find a pattern that when the distance remains the same, but the speed of travel increases, though time taken to reach the destination decreases. When we increase the speed of travel to speed of light, the time dramatically reduces, as shown here. In the next case, it's out of a thought experiment. Let us consider A to B. This is not to travel from house to library, just another thought experiment. Consider 2 points A and B. The line segment, the distance between the line points is 1 inch. Speed of light in terms of inch we have converted, means it will be 1.18 into 10 power 10 inch per second. In 1 inch travel, time taken to reach B from A by the photon at the speed of light is 8.47 into 10 power minus 11 second. That is 0.000000000084745 second. This is absolutely low. So when the distance remains constant and we increase the speed, time reduces. That is natural. But when the distance between objects reduces, when the speed is at the speed of light, the time is absolutely like a frozen. You can see how much fraction of a second it takes to reach from A to B at a 1 inch. So consider less than an inch, fraction of inch, like a 1 by thousandth of an inch, 1 by millionth of an inch. The speed of at the speed of light, the time taken will be very, very, very low. But still, there will be a certain amount of delay for the photon to reach from A to B. It can't be at A and B at time is equal to 0. If it is like that, it won't be a photon. Let's see the next case. Here, from A to B, you see in the diagram it says I'm here at A and I'm here at B. So the same particle is at different positions? No. So consider in the structure of an atom in which electron revolves around the nucleus in certain orbitals. You can't according to Heisenberg's uncertainty principle, you can't exactly tell the position of an electron provided you know momentum. If you know, if you are able to tell the position of the electron, you can't tell about the momentum. So it's like the electron cloud. You can't exactly say electron is here or here or here. So in the form of an electron cloud, you can consider the distance from A and B. The existence of electron can be at any point between A and B. The wave diagram shows the possibility of finding an electron is more at some points and less at some points, but there is always there can be always an electron be at any point on over the line segment. In quantum mechanics, there is another concept. A particle at A is there and another particle is at B, and both are different particles. It is not the same particle which can be found anywhere based on possibility. That is electron case. This is quantum entanglement case. Here uh, every particle has another particle, anti-particle, like electron, positron, neutrino, anti-neutrino, like that. Consider certain group of entangled particles in the point A. There will be entangled particle A, and the similar entangled particles partner will be at B. If you change any aspect of A, like spin or momentum, like that, the same effect will be effect will be visible on the object, on the particle at B. So instantaneously, that is the main, instantaneously there will be no delay. If there is a delay, like a photon to travel from inch, it traveling at the speed of light, there is a delay, but it is not the delay. If there is a change at position A to the particle in t is equal to 0, the same t is equal to 0, there will be another the same similar change will be existing at the particle B. This is possible only if the communication between A and B particles is more than the speed of light, which is violating Einstein's relativity theory, in which speed of light is absolute and it is constant always in the vacuum. So that is why Niels Bohr's quantum mechanics and Albert Einstein's relativity, there will be a lot of argument between them in their ages, and still it is not exactly anyone can't find the difference and understand why it is like that, and what is the flaw in relativity or quantum mechanics. So it is what happening, and that is what it is, and it is quantum mechanics. Thank you for watching. Consider subscribing. Thank you.